This episode, or this video series, is going to be on single loop control methods tuning. We're finally up to tuning. We're going to talk about how do you tune a self-regulating process. Several episodes ago we talked about the process, how to identify it. Then we talked about the controller, proportional integral derivative. Now we're going to talk about how we link these together. This is we're finally at the point where you can actually tune something when we're finished. What's awesome about control tuning is that you get to define how the loop responds. You can either make it respond in a nice smooth transition. If you want to do a little bit of an overshoot, you can do that. Or if you want it to oscillate, you can do that. Simply by changing the parameters of proportional integral. You can take a signal that responds this way and convert it to this. That's what's tuning. You have to kind of know where you want to go with it. And then once you know what kind of response you want, then with the process, you make what you want by adjusting the tuning parameters. That's what we're going to talk about in this particular discussion. You have to decide what you want. And there's a lot of different discussions. If you get into phase leads and gain margins, we're not going to talk about that. We're basically going to say, do you want to have an overshoot, yes or no? And so we'll talk about that. The first one here is called a first order process or a no overshoot. In other words, I change the set point and the process comes right up to it. And we're trying to figure out how to come up with tuning parameters to make that happen. This is the one that I like to use. It's a very stable tuning technique. They will refer to this as direct synthesis. Sometimes you'll have heard it referred to as lambda tuning or pole placement. Those are different names for virtually the same tuning technique. We're going to call it direct synthesis, but it results in no overshoot. I will also quickly talk about the Ziegler Nichols tuning technique in a couple different ways. That's been around since the 40s, and it provides what's called a quarter wave decay. And it's where each positive hump is a fourth. This hump is a fourth of the first hump. It's called quarter wave decay. And so you can come up with tuning parameters to make that happen, and we'll talk about that. Regardless of which method you use, you have to start with the process. You have to look at the process and identify the dynamics of that process. And we spent a whole lesson talking about that. Whether you do a bump test, or you look at first principles, or you do a visual inspection, you have to have an idea of the dynamics of the process. Now, we'll review that in a little bit when we go through this. But once you've identified the process dynamics, then you come up with tuning parameters so that you can either have a fast response, moderate response, or a slow response. The nice thing is that you get to identify that speed. We're going to introduce a new term called tau ratio. The tau ratio is like a knob that allows you to decide whether you want to be fast, medium, or slow. And we'll talk about that when we get into it. The math, and don't gloss over, we're not going to spend time on this, but I just wanted to show you that there is a theoretical background behind the math that is used to calculate these tuning rules. So the way I like to think of tuning is it's a calibration process. If you can imagine your transducer with a zero in span, if a guy's just adjusting the zero in span until it reads right, is he really calibrated the transmitter? Well, most people would say no. Well, if you're just throwing tuning numbers in until it stops oscillating, are you really tuning? My answer is no. You need to understand the dynamics, figure out what kind of result you want, and then use the tuning to match those two. That's called tuning, and that's called tuning setup, and that's what I find fascinating. And it's based upon very rigid theory. And there's another course that maybe we'll do someday on control theory, Laplace transforms and S domains and frequency domains. That's neat stuff, but that's not what we're going to cover today. What's interesting is, as complex as that math is, the tuning rules are really pretty simple. Remember we said in the last clip that the proportional gain and the process gain were inverted? They're inversely proportional. And then there's this term I called tau ratio. I'll talk about that. That's like your knob. If it's a big number, you have a slow response. If it's a small number, you have a fast response. So it's your knob for tuning. And notice we said that the integral time and the process time constant were related. They're not just related, they're set equal. This is why I like the standard form of the PID algorithm. Once you identify the process time constant, that is your integral time. Remember what I said about units. The units that you use for your process identification has to match the units used for your controller. I've had people really mess up. 1 minute and 60 seconds, you could be off by a factor of 60 and not even know it. Well, you would know it once you turn the control on. And if you're dealing with a first order model, which is the most simple model, remember it's the process gain and the time constant, you don't even need derivative. Remember I said derivative's not used very often? The tuning rule, which is the math, when you plug all this stuff together, I have a first order model with a standard PI algorithm, and I have an adjustment of tau ratio where a small number is fast and a big number is slow. Boom, it comes up to this simple tuning. I also just want to identify here that most controllers are in percent. So if you calculate your process gain in process units, then you'll have to convert it to percent. Some manufacturers, that percent conversion is built into the gain. Some it's built into a conversion. Some it's up to you. Just make sure you know how the manufacturer is normalizing the gain. That's all I'll mention here. If you calculate your gain in percent, it's probably going to be right. If you calculate it in process units, you'll have to convert it to percent based upon the range of the transmitter. So that's in the book, and I want you to spend a little more time on that. But in the simplest form, you calculate your process gain and your time constant, and then you pick the tau ratio. Well, the question that comes up is, well, what's the tau ratio? Tau ratio is a ratio of, remember tau is the Greek symbol, tau represents time constant. We're talking about the ratio of the closed loop time constant, which is when I change the set point, how long does it take to get there? Let's say it takes 4 minutes to reach the set point in automatic. But in open loop, if I change the valve, it takes a minute to settle. So the ratio is 4. So that would be a tau ratio of 4. Literally, the tau ratio is defined as how much slower than the dynamics of the process do I want this controller to run. When I was originally taught this method, they said just pick a number, any number will be fine. And I was like, well, it needs to be biased to the dynamics of the process. Don't use the term fast and slow. That's irrelevant. Fast and slow has to be biased to the dynamics of the process. If I'm talking about a tank that has an hour time constant and I tune it to have a half-hour time constant, that's really fast for that control loop. In time, it's slow. But for that control loop, it would be considered fast. That's why I like the term tau ratio, is it biases your choice to the dynamics that you're working with. It really simplifies, and that's what we're going to talk about. If I ever sit down and do tuning with you, you'll see me make a table like this. Usually I pick four tau ratios, 1, 2, 3, and 4. They don't have to be 1, 2, 3, or 4. They could be 1.5, 2.2. It's just a number. But I will make a series. Notice here the integral time stays the same if you're using the standard form. I've kind of been ingrained to think in terms of the standard form. That locks in the time constant, and then you don't have to mess with it. And then your speed of response is strictly a function of the proportional gain. Notice you've already calibrated it to be inversely related to the process gain, and then we got this 1, 2, 3. So literally, the bigger the tau ratio, the slower your response. But slow is now normalized to be in relationship to the dynamics of the process. Let me show you what I'm talking about. If I pick a tau ratio of 1, when I change the set point, I should expect that the ratio of open loop time constant to closed loop time constant to be 1. That's what this is saying. My open loop time constant should equal my closed. That's what a 1 does. So now if I look at the error, subtract the set point and the measured value, you'll get this kind of a, that's the error. So remember what we said, proportional? If you just looked at the proportional component, it would look like this. It's proportional to the error. That's what proportional does. Remember what integral does? Integral is the area under the curve. In the last series, we always showed a step change in the error. Okay, that's why the integral was a slope. But here, the area actually goes to 0. So look at the integral. It comes up and stops. You never get to see the proportional acting by itself and the integral acting by itself. You always see the proportional integral acting together. So you see the output of your controller. So it looks like it was a step change. And a lot of people will incorrectly say, well, it's just a proportional correction. No, it's a perfectly calibrated loop. A lot of times I'll do that is if I think I've got it nailed, I'll pick a tau ratio 1, change the set point, and make sure my output looks like a step. Then I know that the proportional will back off at exactly the same time the integral goes up, looking like it was just a proportional kick. That's what's going on behind the scenes. Now let's look at what happens at a tau ratio of 2. At a tau ratio of 2, your closed loop time constant should be 2 times the open loop time constant. And what that means is it takes twice as long to settle as it did if you just went and changed the actuator. So I change the set point, and it's going to take twice as long. Now if I take the difference here, set point minus measure value, notice my error is taking longer, twice as long, to get to the set point. Notice the proportional. Here I've got them superimposed, but the proportional looks just like the error, and then the integral, remember, you're integrating that area, it looks like this. So when I add these two together, I get this shape. You get this initial kick, and then it comes on up. Notice that the size of the initial kick is half of the total output. That's another trick. If I use a tau ratio of 2 and I change the set point, I will look at the initial step compared to the final step. And if they're not half, I know something's wrong. I messed up my process gain, or I have a nonlinearity going on, or I miscalculated something. There's always a validation step. Most people ignore that. They do their bump test, they come up with their tuning, and they plug it in and they walk away. Don't do that. Change the set point and watch your control work. It should do what you told it to do, and if it doesn't, you missed something. You got the time constant wrong, the gain wrong, there's a nonlinearity, the valve's in a different position. It needs to match. The theory always works. That's the hard part, is the theory is always right. If the application doesn't act like the theory, then you did something wrong. Maybe you got the range wrong. I've seen that happen. There's a lot of cases. So it should do, you're the one in control. You're the one telling the controller how to respond. So if you say a tau ratio 2, the first step should be half of the final, and it should take twice as long to get there than if you just did an open loop bump. Now people say, well, I got to have that P kick. I've got to have it, I've got to lead the process. Remember the example I talked about, getting in a cold car and you turn everything up hot and then you back off on it? Well, how can you do that with a PI algorithm? Well, you have a tau ratio of less than 1. A tau ratio, here's an example of 0.5. It says that my closed loop time constant will be half of the open loop time constant. So if I went and changed the actuator and it took 4 minutes to get there, it would have a 1 minute time constant. Well, if I tau ratio 0.5, it'll have a 30-second time constant, and it'll take, whatever that is, 2 minutes to get there, half as long. Well, how's that happen? Well, same thing. This time I don't show the difference because I think you can see it by now. Notice that the proportional looks just like that error that I had before, and the integral, it doesn't have to integrate as much because the error is so small. And when you add these, look what you get. Your proportional kick is exactly twice where you're going to end up because we had a tau ratio of 0.5. Your initial kick is going to be double, and then it'll race right down, and it should take half as long to get there. This is also what I caution people about. This step is very hard on actuators. It's just hard on that big kick. So I don't like going with tau ratios that low because of this reason. Also, what I would do is do what they call a set point ramp rate. So that instead of doing an abrupt change in the set point, you actually do a working set point ramp rate, and then that reduces that kick whenever you have a large error, because when you have a set point ramp rate, you limit that, so you get a nice lead action. Those are some of the caveats when you go with a tau ratio of less than 1. Now, what tau ratio should I use? That's the question. It's like, well, this is great. I have a knob now that I can spin, but how do I know? Should I go fast? Should I go slow? Should I go, what do we do? This goes back to when we talked about model mismatch. You need to calibrate your tau ratio to your model mismatch, and that's what we're going to talk about here. It would seem that a tau ratio of 1 would be a good idea, because then if you change the set point or change the actuator, they both would get there at the same time. But what about model confidence? What if the process has dead time in it, or is something, you don't really want to be that aggressive? So it's a little bit like an archer shooting, at a target. If he's able to hit the bullseye every time, you don't really need much of a bullseye. But if he's bad like me, he could be all over. You need a big bullseye. Well, think of the tau ratio as a sizing element. And the more uncertainty you have, the bigger the target has to become. So that's what I'm talking about here with tau ratio and confidence. I've got 4 different bump tests that I've done on 4 different processes. So in the first one, I bumped it, and I recommend bumping it, like we talked about in the bump test section, more than once, to make sure that you can predict the gain and the time constant. So you're assuming it's a first order. If your first order model and your process match so that the difference is small, you can get away with a tau ratio 1. That's not a problem. In this case, I've got delay. It may be a first order plus delay, but it's not a first order model. So I have a bigger error, so I should probably go with a bigger tau ratio. It's kind of like if your tau ratio is too small compared to the process, the controller literally starts hunting for it. And a hunting controller is one that oscillates. Oscillations are not good. They cause product instability, product quality, runnability issues, all that stuff. So when you err on the side of your tau ratio being a little bigger. So this isn't a case, typically if you see this, you should stop and fix the problem. Your actuator's broken or your valve positioner's broken. This case, this is a very common one. This underdamped response is that underdamped response, it's actually called overdamped. It's a second order overdamped because there's no oscillation. But the first order, you have an additional lag here. So I wouldn't go with a tau ratio 1 because what happens is this error becomes the valve moving more than it needs to. And I've got a couple of examples of that. So this idea of the arrow. So I do 4 arrows, boom, boom, boom. And if I group, meaning they all hit the same spot, and they hit my model, and my model is a first order. So I'm saying I bump this thing 100 times, it looks the same. It's very predictable, it's very stable. I could go with a tau ratio 1 and it'll be fine. But you have to worry about what happens. What do you think happens when valves wear or instruments wear? They tend to slow down. So as they slow down, you need to adjust your model. So if you have your controller tuned very aggressive and over time it moves out of the window, oscillations occur. So it's better to set your target just a little bigger so that you allow your process to wiggle and you won't get called in the middle of the night. This is a case, I like to talk about this one is repeatability and aggressive tau ratios are not the same thing. In this case, you can see they clustered really, really well, but they are off the tau ratio 1. Tau ratio 1 is when there's no model mismatch. So in this case, we assumed a model to be a first order, but the process is repeatable, but it's not a first order. That doesn't mean you can't tune it with a PI algorithm, you just need a bigger target. The rest of the story there is when you get into advanced levels of control, is not everything has to be modeled as a first order or as a PI algorithm. But that's the topic for a different class. This case is actually the most frustrating case, is where most of the time where I've messed up is I've done one bump test, boom, I said, wow, it's a first order process, and I stop, I tune it for tau ratio 1, and this thing looks great. And then I leave, and in the middle of the night, almost always, the process changes. It's now outside the area that my controller is set up for, and I start oscillating. So when I go back into the site the next day, instead of the nice carpet, warm welcome, they're all lined up with clubs saying, what did you do? And it's usually, I didn't do my due diligence, I didn't pay attention to the process, and it moved outside the window that I had tuned it for. That's why I recommend bump tests. That's why I recommend an electronic log or a log of some sort to cover yourself. Say, when I bumped it, this was the model. Another example, I was at a place, I bumped this thing a bunch of times, and I got the same model every time. And I tuned it and solved a problem that had been around for a long time. The next day I came in, and it was all over the place. And they said, I told you it wasn't going to work. And I said, well, this control theory, it just doesn't break. So I said, let me go back and do another bump test. So we did a bump test on the same process, but the parameters were completely different. So I brought the process, I said, look at this. I said, yesterday this was the process, today it's this. They're completely different. What happened? Well, it turned out they had different lines were running, and when one line would run, the dynamics would change. When 2 lines would run, you'd get a different dynamic. This had been going on for the history of this particular plant. we simply put in gain scheduling. Say, well, when both lines are running, use these gains. When one line's running, use these gains. And it solved a persistent problem that had been going on for years because of this. If you can calculate or predict what causes the model to change, you can adapt for it. But it's knowing what control can do, knowing how to calculate the process, and you can get it. So, bigger targets, it is a little slower, but it's more stable. So, I usually will make this chart, and if you look in the back of the book or some of the reference, you'll see these, or you can make a spreadsheet. I always pick a couple tau ratios. In my head, fast as compared to the dynamics of the process. A 4 is slow as compared to the dynamics of the process. If you're using a standard PID algorithm, the TI and the time constant are the same. Make sure that the units that you're using for the dynamic and the units for the integral are the same. And then the control gain is inversely related to the process gain, and then the tau ratio changes the speed of the response. Keep in mind scaling. There's several different controllers out there that integrate the range of the transmitter into this or not, but that's something that you can identify when you look at the documentation. So here's an example. We walk up to a unit and we do a bump test. And so you can see, here's my set point, here's my output change, the control's in manual, and I've got a process response. So now I've got a bump test and there's my response. So now what type of process is this? Go back and remember there were 6 areas. There was pure gain, first order, second order overdamped, second order underdamped, first order plus dead time, integrating process. Which one is this? This happens to be a second order overdamped process. That's the classification. We're still going to assume it's a first order process. And this is going to take you a little while. I recommend you do it by hand, but there's a lot of tools. We have software that will model this for you. But I recommend that you start calibrate your eye to what a first order process looks like. So the process gain is the change in the process over the change in the output that produced it. So in this case, we made a 15% change, which is huge, and a 25% change in the output. So I got a gain of 1.67. Boom. I like to do a couple different bump tests to make sure that 1.67 is consistent over the operating range of my process. This is very, it correlates well to valve position. I've been in other places where, if your valve, that 60-10, 90, that 30-60-90-10 rule is that between 30 and 60% of your valve, you get 10 to 90% of your range. Is pretty accurate. Between there, your process gain is well constant. On the ends, your process gain can be really, really different. And that's why I like to look at my valve position when I'm getting ready to do this change, this bump test, or over history. The other thing you want to do now is calculate the time constant. Basically, I like to take, when did this thing settle, call that the dynamic transition time, and divide that by 4, or the dynamic settling time. So in this case, it took roughly 50 seconds divided by 4, that's 12 and a half. So 12 and a half seconds. Remember the other techniques we talked about is divide this in thirds, and where the 1/3 part is, that's roughly 63 or 66%, that's 2/3. That's a time constant. So total time divided by 4, or break it into thirds and find out where it crosses, that's your time constant. Error on the side of being big, and it induces stability into the system. So now we have the time constant of 12 and a half and the process gain of 1.67. Then I fill in this chart. Well, before I fill in the chart, I kind of estimate what's the model mismatch. I said, well, it's not a pure gain, or it's not a first order process, but it's close. So right off the bat, you shouldn't be thinking tau ratio 1, but it's not too far off. So start with a tau ratio 3 and see how that looks. So in this case, I fill in the chart, tau ratio 1 through 4. Notice my gains, 0.6, 0.3, 0.2, but my integral time's the same. We applied the tuning rule that I showed you earlier, which comes from a mathematical proof or derivation. Then we do a bump test, the validation step. Don't forget the validation step. So we start with a tau ratio of 3. At a tau ratio of 3, what you can see is we change the set point, and remember at a tau ratio of 3, how big should this kick be as compared to the total? 1/3. So you can see that that's 1/3. It's very stable, but maybe it's a little on the slow side. So let's try a tau ratio of 2. Tau ratio of 2, you can see the initial kick's half, then the total. That's not bad, actually, tau ratio 2. So then we start at tau ratio of 1. Uh-oh. Now people may say, well, that looks really good. I said, yeah, but it's not doing what I asked it to do. And so why is there an overshoot? Look at the valve. It had my proportional kick was boom. So if you notice, the original step and the final step is the same, but it did all this gyration. Where'd that gyration come from? Remember model mismatch? It came from, I hate to do this, but this area right here. This, if you look at this shape, this model mismatch, take a picture of that in your head and then go over here. It's the same thing. The model mismatch shows up in valve searching for the process. That's bad. That's unstable. And so eventually it's going to break. So for me, what I would do is say, well, let's take a look at this. At a tau ratio of 3, it was very stable. A tau ratio of 2 still looked good. Tau ratio of 1, I just crossed over where I would feel comfortable with this loop. So basically, a tau ratio of 1, the process is very repeatable. But a tau ratio of 1 is just a little bit oscillatory. Not bad. But a tau ratio of 2, there is no overshoot. And a tau ratio of 3 is even better. So then you could make a decision. It's like, well, maybe take a 2.5, and then you're done, and you don't have to worry about it. And then if someday in the future someone says, hey, that loop's breaking, then do another bump test. Make sure that the gain and the time constant are the same. They probably aren't, because that's what changes over time, is the dynamics are what change based on a lot of different conditions. And so you may have to update your tuning, but then you would have a method to follow. Now, what I like about direct synthesis tuning is it's very stable. It's based on the process, and you get to pick the speed of the response. That's what's exciting about direct synthesis, is you pick you say, I'm going to assume all processes that are self-regulating are first order, which means there's a process gain and a time constant. I'm going to use the PI algorithm, and I'm going to pick a tau ratio that will adjust the speed of the response. You pick the speed of the response as a function of model mismatch, and you can tune your loops. Now, very quickly now, I want to show you the Ziegler Nichols, because that's one that's still presented at college. It came out in the 40s, and it was designed to have, warships follow airplanes in the sky. So at that time, these big gun turrets were having a hard time shooting airplanes out of the sky. And they came up with a method to tune those so that they could track an airplane, and when they zeroed in on it, if it sent a spray of bullets, it was more effective. That was designed in the 40s, and it was called the Ziegler Nichols. That's the name of 2 guys that actually worked for Taylor Instruments, which is now part of ABB. So a long way, we've had a long heritage of ABB work. ABB has had a long heritage in automation and tuning solutions. But it was developed in the 40s, and it's designed to give a quarter wave decay, but it still starts with a process. Now, if you take yourself back to that time period, there wasn't electronic controllers. There really wasn't even that much. The pneumatic controllers were just getting started. I've seen some of those controllers. There was knobs. There weren't numbers like we have today. So the idea of tuning by feel, you really could feel when you got it right. That was the idea, and it's still taught in schools today. There's a couple different steps that they've modified, and it's called the ultimate gain method, where you set the integral to 0, you cause a disturbance, well, here's the picture, and you start adjusting the gain until you get a sustainable oscillation. Once you've got, so when I've tried to do this, I pick a gain, I change the set point. If it's starting to attenuate, I know that it's I don't have the right gain, or I don't have the ultimate gain. Then what I do is I increase the gain and say, oops, this is going unstable. So then I know I've got the gain somewhere between there, and I can then figure out how to make a sustained oscillation. Once you have the gain that produces a sustained oscillation, then you plug in your ultimate gain. If you're using a P-only controller, you do this. If you're using a PI controller, you do this. And if you're using a PID, and what this will do is it'll give you that quarter wave decay where it'll oscillate. Again, the questions that come up from your operators will be, well, how much of an oscillation will I get? Well, I don't know. It depends. Well, how long will the oscillation take? Well, I don't know. How much will the output move? And you're like, well, I don't know. And unfortunately, that may be the last bump test you get to do. So that's a hard one to do in industry today. But there's been techniques where they do clipping circuits until you get a square wave. And then there's this one called the point of inflection, where you actually do a bump test. And then you try to figure out where is the point that the slope goes from going up to a slope going down. That's the point of inflection. You draw a line through there and you calculate the slope and you calculate the delay, and then that goes into here, this equation. But they're all designed to give you a quarter wave decay. Some industries that are slow moving, or I will say that when you're doing a tracking error, where you're trying to track a set point that's moving, this does produce the smallest, what they call velocity error. You can keep up with it. It's just when you stop, it's going to ring. That's the drawback. Direct synthesis, it's more designed the way industrial plants operate. Set points, so it's more stable. You do one bump test, you look at the physics, and you can calculate the tuning parameters. So my bias is towards the direct synthesis technique. But my point here when we're wrapping up is tuning isn't just throw in some numbers and see what happens. I hope you're seeing that what we're doing is we started with the process, and we're trying to match that process to the controller. You do a bump test, you calculate the model, you use the tuning rules to come up with tuning, and boom, you have a very stable process to come up with loop tuning or tuning of your plant. And what that will do is result in money for you. You'll have less downtime, you'll have less defects, you'll have higher production, higher quality, and a more stable plant. A more stable plant means they can run faster, run longer, and have a better product at higher quality. That's the trick. Loop performance and automation services for today make this a reality if you know what you're doing. Start with the process, understand your controller, link the two together, and you hit a home run every time.